Let's solve this GATE question related to ISAM indices. GATE 1993 paper. An ISAM indexed sequential file consists of records of size 64 bytes, each including key field of size 14 bytes. So finally you understand that each record size 64 bytes, pixel length records. Usually in GATE problem they give pixel length records problem, then only problems will be easy to solve. Second thing, key field of size 14 bytes. Let's write that. So key is 14 bytes. This is key. This is record size. Now slowly we understand the data. An address disk block takes 2 bytes. That means address of disk block takes 2 bytes. So we write that. So 2 bytes for disk block. I can say that block pointer. Now if the disk block size 512 bytes, so disk size is also given. So block size is 512. We write all this data so that calculations will be quick for us. Now after that there are 16k records, right? Number of records 16k. What you do is stop the video and read the question clearly and note down all this data given, which is important for us. Then you try to solve this question on your own. If you cannot, then please see the solution. So in that way, so it will be better for you. Compute the size of the data and index areas in terms of number of blocks and how many levels of tree you have to construct for the index. Two questions they are asking. First of all, how many blocks are required for constructing the index? Second one, how many levels are there in the tree? First of all, please recall what is ISAM index. In ISAM index, there will be data records first, correct? All your data will be created as nodes. What is the node size? Node is nothing but block, right? From now onwards, you remember in entire indexing, usually or if nothing is given, page equal to block equal to node, anything. Okay, so since we are dealing with now trees, so every tree node will be usually kept in one block. So now we know that in ISAM index, first of all you will have leaf pages. Our target is how many leaf pages we have to construct for our file. For that you should know the blocking factor, otherwise, so usually we say blocking factor, that is nothing but block capacity. Ask yourself what is the block capacity of our problem. In a problem, block capacity is 512 bytes, correct? Then with respect to number of records, how many blocks, how many records we can keep in a block. So first of all we understand that, so in your block what are the things we keep in leaf pages? Recall, in leaf pages I told you that keep all the records followed by just extra pointer. That extra pointer should point to what? Overflow pages, right? Since only one pointer we are going to maintain and especially that is only 2 bytes space, so we can ignore that one so that calculations will be easy for us. What is my strong feeling is that 2 bytes does not affect our answer. So what you do is you answer same question with adding the 2 bytes also. That means, so now since you are adding 2 byte pointer, then effectively your block size 510, then in that 510 how many records we can keep, you calculate. Okay, so it will not add any effect. Let me solve this problem by ignoring these 2 bytes. So if that is the case, then your 512 bytes block is going to accommodate records. How many records we have? The number of records are huge, 16k. But what is the capacity of a block? For that you should know the size of the record. Since size of the record is 64 bytes, then we divide like this. 512 is your capacity, 64 is actual record capacity. Then this is called actually blocking factor, otherwise branching factor, everything. So 8. So for us it is nothing but block capacity. So let's say it is 8. Now I can say that there are 8 records in the block number 1, another 8 in the second block. In that way, if we keep, how many records we can keep in overall blocks? That means how many blocks are required to store all these records? Very simple. So you know the block capacity, then divide it by, divide using that 16k. That means take 16k, these are all number of records, and divide it by one block capacity. Number of records is 8, right, for in block. Then you get 2k. So this 2k is nothing but number of blocks are required to store leaf pages. Now we got one important thing, that is the number of blocks in the leaf level, they are nothing but 2k. Remember it. That means 2000 48, right? K means 1024. Now what we do in the process of ISAM creation, we create index pages, right? So how many index pages we create? We don't know. It depends on number of leaf pages. So I will tell you what is the relation between these leaf pages and index pages. First of all, we should know what are you going to do in this index page. That means what are the things you are going to keep. We keep some keys. So please recall our ISAM tree. In the ISAM tree, in index pages, we have some keys and pointers. How many keys we have, how many pointers, I will remind you. So in our diagram, so we had like this two keys, right? So something like 20 comma 30, and we had three pointers. 20 is left, in between 20 30 and 30 is right. So if you understand that point, then we can understand that. So in a index page is nothing but index block. In each index block of next level, we are going to keep some keys. How many keys you don't know? Let's say it as k keys. And what are the other things you are going to keep? Whenever we keep k keys, then the number of pointers we are going to keep is k plus 1, right? That is what just we learned. Now k plus 1. Anything else? We don't keep anything else. Just we keep keys and the extra pointers to index to these leaf pages, right? So how many? K plus 1. All these should fit in one page. Page means block, block means 512. We have only 512 bytes capacity for each block. In this 512 bytes, we have to keep k keys. If I keep k keys, how much space it occupies? K is a variable, we have to find out k value. So what is the how many keys, what is the size of the key? Size of the key is given as 14 bytes, right? K into 14 plus anything else? K plus 1, tree pointers, otherwise block pointers. Since your tree pointer here is nothing but we are pointing to a block, right? Block pointer. So what is a block pointer here? Block pointer size is 2 bytes. So let's add 2. So finally k into 14 plus k plus 1 into 2, this entire thing is the capacity of your node. That should be less than or equal to 512, because we are going to keep all these things, these k keys and k plus 1 pointers in one block. That's why that should not exceed 512 bytes. That is quite obvious, right? Now let's simplify so that you get k value. So I will tell you what is the meaning of k. Let's simplify it. So you get 14k plus 2k plus 2 less than or equal to 512. Then it would be 16k less than or equal to 510. Then k will become less than or equal to 510 by 16. Then if you simplify it, you get 16 3 is a 48 and 30, 16 1, 31 point something you get. Remember, that means number of keys you can accommodate maximum in a block equal to only 31 point something. However, we can't keep 31 point something. Then if we go for lesser value, it will be 31. However, we can't keep 32. Don't say if you get 31.9, don't say 32. Even we cannot keep, greater value than 31.9, anything like even a small value also 31.95 also we can't keep, right? However, 31.95 keys cannot be possible. That is also one more point. So either we can keep 31 or 32. Otherwise, that is what your subject, right? So 31 or 32 is your question. We can't keep 32 because k value should be less than or equal to 31.9. So it should be obviously 31. So why not 30? Yes, you can keep 30, 29, but maximum keys. When I can keep 31 keys, I will go for 31 keys. The reason if I keep 31 keys, then there will be 32 pointers. Then 32 pointers are going to, each pointer is going to point to one leaf page. That is what the concept, right? So let's do that. So finally what happened so far? We have some leaf pages. We realized that the number of leaf pages are 2k. To point all these leaf pages, we need some index pages. How many index pages we want, I will tell you. If you have one index page in the next level, that is going to have 31 keys maximum. If it has 31 keys, so you are going to have 32 pointers. Remember it. Now here also 32 pointers. Now ask yourself, but I want to hold 2k nodes. Each pointer is going to hold one node. Then how many pointers are required? Simple. So 2k nodes are there. One pointer is required for one block. We have 2k blocks. Simply divide by number of pointers in each block. I will tell you the reason. If you do that, you will know how many blocks are required. So I can say that this is branching factor. So this branching factor 32 is going to help you to know how many blocks are required. Each block is a tree node, right? So this blocks branching factor, that means in a block we have pointers, so that is 32. So that 32 is going to decide the number of nodes in this level. It's very simple formula. Divide that 2k nodes by 32, then you will understand how many such 32s you want. So if I simplify it, you get 2 into 2 power 10 by 2 power 5. It would be 2 into 2 power 5, which is nothing but 2 power 6. So that means we need such type of 32s 2 power 6. 2 power 6 is nothing but 64. So finally we understand that we need 64 blocks. If we have 64 blocks, each block will have 32 pointers. 64 into 32 will become 2k nodes. So we can point them. So this is next level of indexing. In next level of indexing, how many finally blocks we have? Just now we calculated 64. What is the formula for that? Simple. Whenever from now onwards you get this kind of situation, so where there are 2k nodes and each pointer points to one node, each block has only 32 pointers, then how many such blocks you want? Simply 2k by 32. But I don't prefer remembering the formulas that unnecessarily mess up the things. So just understand the concept so that it will be easy. So what is our target next level? In the next level, again we have to know the number of index pages. What is our target for what is actually our target? Our target is pointing to these these level nodes, right? There are 64 nodes. You tell me to point 64 nodes, how many pointers we need? 64. But one box, these are all boxes are similar boxes, then you don't need to check again. So here the capacity of each box is 31 keys and 32 pointers. So one box can have 32 pointers, then another box can have another 32 pointers, finally 32 and 32, 64. So that means two blocks are enough in the next level, correct? So I can say that in the next level you need two blocks, otherwise divide this 64 by 32. See, 2k nodes and divide that by 32, you get next level blocks, and the next level blocks are 64. Divide by 32, you get next level blocks, and this time you divide simply 2 by 32. Then you get something 0.00. That means what? Just a small box is enough, but we can't have small box, right? Only fixed size blocks we have. So one block we have to take. I can say that one block is necessary. So finally, we have two questions. One is compute the size of the data and index areas in terms of number of blocks. So let's do that. So with respect to number of blocks, how many data blocks we have? These are all data blocks, right? Last level where we keep the data. This entire thing is index. So 2k data blocks, DB. Now how many index blocks we have? So in the first level 64, plus in the next level it is something around 2, and in the next level it is 1, right? 67. Now the second question, how many levels of tree you have for the index? So this is actually tree, especially is asking for how many levels of the tree you have for index. So this is index, this is data, right? So let me divide that into two parts. This is data area, so usually in ISAM, and this is index area. So in index area, how many levels we have? 1, 2, 3. So that's why second answer is 3. That's it.